Hello student, this video lecture is prepared for heat transfer subject, unit number 4, condensation and boiling. In last lecture, we have discussed these points: heat transfer in condensation of single vapors, dropwise film condensation, difference between dropwise and filmwise condensation. In this lecture, we will discuss how to calculate the heat transfer rate in filmwise condensation. Then we will discuss some problems depends upon that filmwise condensation. And at the last, we will discuss effect of non-condensable gases on the condensation process. So here we have concluded last lecture, that is difference between dropwise and filmwise condensation. Then you have to look at this table number 3.3, which gives the average value of film coefficient, that means heat transfer coefficient, for condensation of pure saturated vapors on horizontal tubes. So if the tube is maintained in a horizontal direction, so at that time what are the average values of heat transfer coefficient for different vapors and their temperature range is shown in this table. So first column shows that what are the types of vapors: steam, benzene, methanol, ethanol, toluene. Then for that vapor, second column indicates HM, that means average value of heat transfer coefficient in watt per meter square Kelvin. So here 10,000 to 28,000, 18,000 to 37,000. So these are the range. Delta TF is nothing but the temperature difference between that saturated vapor and wall. So that is called a delta TF. So these are the temperature range. So for benzene, it is having value 1,400 to 2,200 in the range of 23 to 37, etc. So why I am showing these values? Because if we look at the values of heat transfer coefficient when there is no phase change, so these values we have discussed already in a convection chapter. These values are around, for example, water up to 300, 400 watt per meter square Kelvin, organic chemicals 300, 400, 500 watt per meter square Kelvin. So these values are low as compared to when the phase is changed. So when the phase is changed, the latent heat is taking place. At that time, the heat transfer coefficient is very high as compared to the sensible heat. So where the heat is transferred in a sensible heat, at that time heat transfer coefficients are low. So for that purpose, I had shown this table for the different value. So from this we can conclude that when the heat transfer taking place in a latent heat, or whenever there is a change in a phase, maybe liquid to vapor or vapor to liquid, at that time heat transfer coefficient and heat transfer rate is also high. Then here we will discuss correlations for filmwise condensation. So in last lecture I had told that generally we are using the filmwise condensation in a chemical industry, because for dropwise condensation we do not have any calculation method. So for that purpose we have discussed filmwise condensation only in this chapter. So for that purpose we have to first we want to calculate the mean heat transfer coefficient for two types of a surface. First one is the vertical surface and second one is the horizontal surface. So in chemicals industry, we find both the surfaces, means vertical surface, sometimes maybe their vertical plate or maybe condenser in a vertical position, and sometimes it may be in a horizontal position. So both cases we have to first calculate the mean heat transfer coefficient by using different formulas, and then we have to calculate the rate of heat transfer, and then we can calculate the mass flow rate of that condensation. So first we will discuss for vertical surface. So suppose the vertical surface is like this. So the condensation is taking place in this manner. So for that purpose we have to use this formula. Hm is equal to 0.943 under square bracket rho square g lambda k to the power 3 divided by mu L delta Tf square bracket complete, and whole bracket is having power 1/4. So here this is the constant, then rho is the density of this condensate, g is acceleration due to gravity, that means gravitational acceleration, which is equal to 9.81 meter per second square. This lambda is nothing but latent heat of vaporization. Then K is the thermal conductivity of this liquid. Then mu means viscosity of this liquid, and L means this length of the tube or that surface. Then delta Tf is nothing but the temperature difference between vapor and metal. So what is the temperature of this vapor and that metal is delta Tf. So you have to put all these value in this equation and calculate the Hm. And sometimes your that surface or your tube may be horizontal. In that case you have to take outside diameter, that means d0. So this diameter is d0, outside diameter, and you have to change that formula, that is Hm is equal to 0.725 into bracket rho square g lambda k to the power 3 mu into d0 into delta Tf square bracket complete to the power 1/4. Okay, so if we look at this figure, so this is the horizontal tube and these are the condensation or vapor condensation, and black portion shows the tube. So you have to take the outside diameter d0 here, and these are the vapors. So vapors are condensed outside of that tube. So here we have to just replace this formula by using constant, that is 0.725, and again you have to replace that L here, d0. So here we are using L, but in this case you have to use the d0, that means outside diameter of that pipe. Then how the heat transfer coefficient is calculated in condensation. So we have to use this formula. Q is equal to HMA into bracket multiply by into bracket T saturated minus TW. So these are the temperatures. So HM is nothing but this mean heat transfer coefficient, maybe vertical or maybe horizontal, depending upon the problem given. You have to put this value, then calculate the area. Then T saturation means saturation temperature of this vapor. So this vapor is having some saturation temperature, that we have to write here. And TW is nothing but the wall temperature, so surface temperature. So obviously the surface temperature is low in this case. Note that this temperature is higher, this temperature is lower. So you have to just minus this quantity, multiply by the area of that surface, maybe plate or tube, whatever it may be, and then you have to calculate the HM. So HM will depend upon how the surface is placed. If it is a vertical, then you have to use this formula. If it is a horizontal tube or horizontal, then you have to use this formula. Okay, just you have to change this value. Okay, and Q in both cases we can calculate using this formula. Then sometimes you have to calculate the mass flow rate of that condensate. So how many mass flow rate is obtained from that condensate. So for that purpose you have to just put the value of this Q here, and the lambda is, that means latent heat of vaporization is given in that problem. So you have to just put that value and we will obtain the mass flow rate in kg per second or kg per hour. So we will look one problem first. So here the vertical plate 30 by 30 centimeter is exposed to steam at atmospheric pressure. I will read the problem first. The plate is at 371 Kelvin. Calculate the mean heat transfer coefficient and the heat transfer rate and mass of steam condensed per hour. And in the data it is given that the properties of condensate at film temperature, that means that temperature at which this film is occur, at that temperature, that is known as film temperature. So density is given, viscosity, thermal conductivity, latent heat and saturation temperature of steam is given. And additional information is given that assume that the condensate film is laminar. So what is the flow type in that vertical condition is laminar flow. So that means Reynolds number is below 2100. So there is a plate. So here this is suppose that plate 30 by 30 centimeters. That means these are the distance 30 by 30 centimeter is exposed to steam at atmospheric pressure. So steam is coming from this side and the steam temperature is 373 Kelvin. So this is the steam temperature, and suppose the other side of this surface is maintained 371 Kelvin. So this is the another side temperature 371 Kelvin. And for this case we have to calculate the mean heat transfer coefficient, heat transfer rate and mass flow rate or mass of steam condensed per hour. So the properties are also given. So this is the vertical surface. So you have to just use the formula, this formula, Hm is equal to 0.943 into bracket rho square G lambda K to the power 3 L mu delta T. So here delta T is nothing but difference between this and this, 371 minus 371. Sorry, 373 minus 371, which is equal to 2, and we have to take the power 1 by 4 and multiply by 0.943. So we get this answer 13150 watt per meter square Kelvin. So this is the HM, that means mean heat transfer coefficient for this vertical plate. Then we have to you have to calculate the heat transfer rate. So that is Q. So Q is calculated by this formula. HM is HM multiplied by A into T saturated minus TW. So T saturated is 373, TW is 371, and HM we have already calculated here. And you have to just put the area. So the area for this plate is you have to convert this centimeter into meter. So 0.3 multiplied by 0.3. So this is the area. So that area we have put here and calculate this quantity. So we have obtained Q is equal to 2367 watt. Then from this we have to calculate the mass flow rate or mass flow of the condensate, which is equal to Q by lambda. So Q we have already calculated here, and the value of lambda is given here, but this value is having in a kilojoules per kg. So that we have to convert into joules per kg, multiply by 10 to the power 3. So here we are obtaining the answer in kg per second. Okay, so unit of Q is given here, watt is nothing but joules per second, and unit of lambda is given here. So joule get cancelled, kg per second. But in the problem it is asked that you have to calculate the condensate rate in per hour. So just multiply by 3600, we get 3.78 kg per hour. Okay, so in this way we can solve this problem by using this formula. So thanks for watching this video. We will discuss the remaining part in the next lecture. Thank you.